Hello, welcome to Basics of Finite Element Analysis. Today is the 4th day of the current week, which is the 6th week. And in our last class, we had discussed as to how to develop interpolation functions for Euler-Bernoulli beam elements. Today, we will actually use those interpolation functions to construct element level equations for an Euler-Bernoulli beam, and maybe also talk a little bit about the assembly procedure for these element level equations. So, we will develop finite element model for Euler-Bernoulli beam. So, our overall equation for an element is a stiffness matrix times generalized displacement vector equals a generalized force vector, and where force vector is itself made up of two components, contribution due to distributed normal force and contribution due to point forces and moments. Now, Kij, so K, so if I have a two noded element, then there are 2 degrees of freedom here and there are 2 degrees of freedom here. So, the size of this K matrix will be 4 by 4, total number of 4 degrees of freedom. So, Kij equals 0 to He B, which equals E times I times second derivative of phi, and actually again it should be a total derivative So, that is my definition of the ijth element in this K matrix. F I equals integral on the domain of phi E times F, which could be a function of times dx. And then of course, I have q1s, q2, q3, q4, which I have already defined, which constitute the K vector. So, in an overall sense, I have K11, K12, K13, K14, So, this is my stiffness matrix for the eth element. And the way I will calculate each element is using this formula, and in this phi I and phi j will be the interpolation functions which we discussed in the last class. So, we will use those phis as the interpolation functions. So, that is how I will develop my K matrix. You please note that this K matrix, I will once again state, it is bilinear in phi I and phi j, and it is also symmetric in phi I and phi j. So, if I replace phi I with phi j and phi j with phi I will get the same value, which means that Kij will be same as Kji. So, K matrix is again symmetric, and it is primarily coming because my B functional was bilinear and symmetric. So, this matrix is multiplied by a generalized displacement vector which are u1, u2, u3 and u4. Okay. Physically, u1 represents w at 0, u2 represents slope at 0, actually negative of that, u3 represents w at he, and u4 represents negative of slope at he. But in our computational algorithm, we do not differentiate, we just put u1, u2, u3 because it is easy to program. So, this equals a force vector F1 plus Q1, F2 plus Q2, F3 plus Q3, F4 plus Q4, and there is a superscript E at all of these because this is for the eth element. Here F's F1 and F3 represent shear forces at specific nodes due to distributed load Q. And F2 and F4, they represent moments, bending moments, again due to distributed load. Again at the nodes. So, you have a distributed load and its contribution at node 1 and node 2, that is what F2 and F4 represent. And then Q1 and Q3, they represent shear forces at the extreme points of the element Q1 and Q3, and Q2 and Q4, they represent point moments at the nodes 1 and 2. So, F's, they represent consequential shear forces and bending moments due to distributed load, and Q's, they represent shear forces and bending moments due to point forces. If these point forces are absent, then when we do the assembly process, these things will vanish. Okay. If I do the math and use all these interpolation functions which we discussed earlier in the last class, then my stiffness matrix and this F matrix or F vector, it looks something like this. So, K equals 2B over H cube. For the moment, I will just drop that superscript E for purpose of convenience only, and these values of terms inside the matrix are something like this. And my F vector is so I would like you to note two things. This row, the second row, and the fourth row, they have the same terms. Same thing is here also, second row and fourth row, they have the same terms. And then the first row and the third row, they have the same terms, both on left and right side. And the reason for this is, you may have already guessed, that the second row corresponds to rotational degrees of freedom and they are associated with moments. So, it does not matter whether you are looking at node 1 and node 2, whatever is the rotational degree and associated bending stiffness of the element will be same, right. The first term, first row and the third row, they are associated with the displacement and they are related to displacement. So, that is why they look similar. The same thing on the right side of the equation also, that you have same terms there. So, even though these things in the u vector, they are generalized displacements, but physically they are different entities and the dimensions of elements in the second row and fourth row are different than the dimensions of elements in the first and third row. So, you should remember that. So, when we do assembly, we have to make sure that we do not accidentally assemble second and third row or first and second row, because they are dimensionally different entities. So, next what we will do is, we will start discussing the assembly procedure. We will start discussing the assembly procedure. So, suppose in this case what we will assume is that I have this is the beam, I am breaking it up into two elements, this is first element, this is second element, and the global degrees of freedom, global node numbers are 1, 2 and 3. The global degrees of freedom are u1 and u2, u3 and u4, u5 and u6. Locally, the local degrees of freedom, okay. So, before I write these degrees of freedom, local nodes are 1 and 2 for first element and 1 and 2 for second element. So, this is all global and this is all local. So, these are the node numbers and the associated degrees of freedom are u1 1 and u2 1. Associated with this, I have u3 1 and u4 1, right. Associated with this, I have u1 second element and u2 of second element, and associated with this degree of this node, we have u3 second element and u4 second element. Okay. So, at this node, this degree of freedom is equal to this degree of freedom at the common node, and this degree of freedom is equal to this degree of freedom. So, the conditions at the common node are u3 1 equals u1 2 and that equals my global degree of freedom, which is u3. Similarly, u4 1 equals u2 2 and that equals u4. And because I am equating these two conditions, these are the conditions for continuity. and of course other conditions when I am doing the assembly, eventually I will replace U11 by U1, which is the global degree of freedom, U21 by U2, and then at node 3 it will be U32 by U5 and U42 by U6. So, I will rename these in the at the assembly level, these things. So, I have these are my continuity conditions. Okay. The other condition at the common node is that the total force at this common node from element 1 plus the total force from the side of element 2, that if I add them up, that will be the actual force at node 2, right. If I just look at element 1, I will have only partial contribution of the load. So, if I am looking at the assembly level, total load from side 1 and total load from side 2, if I add them up, then that will be the total force at, so force balance. So, what are the equations for force balance? F31 plus F12, this equals F3. Similarly, for the moment, so this is about shear force F3, and then for if I have to add up moments, then F41 plus F22 equals F4, that is the generalized force which is moment. And then when I look at Q's, Q31 plus Q12 equals Q3 and Q41 plus Q22 equals Q4. So, these are the equations for making sure that we account for forces correctly. So, what we will do is that in the next class, we will write down the equations for both these elements, and then using these relations actually assemble those elements, so that you can understand how this actual assembly process is going to happen. So, thanks a lot, and we will meet once again tomorrow. Thank you.